Assalamualaikum. My name is Shazwani Najwa. Me and my friends will explain how to determine copper in rose tea sample using flame atomic absorption spectrometry. First of all, the objective. This study aims to establish a reliable and efficient analytical approach by integrating emulsion liquid-liquid micro-extraction with FAS. For accurately measure copper concentrations in rose tea samples. Now, how about we explore flame atomic absorption spectrometry, or FAAS, an important technique used to measure the concentration of metal elements in a sample. FAAS works by measuring the light absorbed by atoms that are vaporized in a flame. So, this light absorption helps us to determine the concentration of specific metal elements present in the sample. So, in the flame, atoms absorb light of a specific wavelength. So, this wavelength corresponds to energy needed to excite the atom's electron to a higher energy level, which is a key to the measurement. To make accurate measurements, we need to calibrate system using standard solution with non-concentration. So this helps to create a reference curve that we use to compare and determine the concentration of our samples. After passing through the flame, the transmitted light is measured by a detector, often a photomultiplier tube. So the absorbance at the specific wavelength directly tells us the concentration of metal ions in the sample. Now let's take a quick look at how flame atomic absorption spectrometry works. First, we start with a liquid sample. This is the sample that contains the metal we want to measure. Next, we introduce the sample into a flame. The heat from the flame turns the metal atoms in the sample into a gas, and light shines through the flame. This light has a specific wavelength that only metal atoms can absorb. Finally, we measure how light passes through the flame. The more light absorbed, the higher the concentration of the metal in the next emulsification, liquid-liquid micro-extraction. Simple but effective process used to extract substances from liquids. So first, we have emulsification. This is where we mix two liquids that normally don't mix. The extraction solvent, which will pull out the target substances, is spread evenly in the water-based solution. We use a dispenser solvent to help with this. Now comes to the extraction. The substance we want to measure, known as the analyte, move from the water phase into the organic phase where it can be separated. Okay, what makes this process efficient is the micro-extraction technique. We use just a small amount of solvent to do the job, and this can save resources and improve accuracy. Okay, when we add the extractant to the solution, it forms a fine emulsion, meaning tiny particles suspended in the liquid. Emulsifiers are used to reduce the tension between two liquids, help this process happen smoothly. Now we continue to the process of preparing rosebud tea sample for analysis. First, we weigh 2.2 grams of two different brands of rosebud and place each into 200 ml flask. Then we fill each flask with drinking water up to 200 ml mark. So brew the tea at equal to room temperature and transfer into 30 grams of brewed tea into clean bottles. Next, we dilute the tea with ultra pure water, bringing the total weight in the bottles to 300 grams. And we add copper solution to the bottles for matrix matching calibration and adjust each sample to final weight of 40 grams. Finally, we pipette 8 ml of each spike sample into centrifuge tube and perform the extraction method for analysis. For the result, let's see the performance of the method used for detecting copper in solution. Okay, under optimal condition, FAAS demonstrate a dynamic range of 0.49 to 9.96 mg per kg with a high calibration accuracy of R squared equal to 0.9999. The limit of detection, LOD, was 0.12 mg per kg, and the limit of quantification, LOQ, was 0.41 mg per kg. Next, using the enhanced method, we achieved a better result, a dynamic range of 5 to 250 microgram per kg, calibration accuracy of R squared 0.9992. As we compare to standard FAAS, the method improved detection power by 50 times and calibration sensitivity with 40 times. In our study, we analyzed 2 rows T samples using FAAS. After applying, we developed micro extraction on method. Initially, no copper detected in the sample, so we performed spiking experiments to test the method's accuracy. Okay, copper solution being added to the T samples, FAAS equipment in action. We spike down amount of copper into the T sample and analyze them under optimized condition. The first result showed recoveries between 66.4% and 74.4%, indicating matrix effect. Next, to improve accuracy, we use a metric machine calibration strategy, which is increase recovery rates to between 96 to 118%. This approach ensured more reliable result for both T brands. Finally, we calculated the analyte concentration for each T brand using the corresponding calibration plots. This method ensures a better accuracy and consistency in real-world testing. Discussion. In this study, flame atomic absorption spectrometry was used to measure copper in rose T sample. FAAS is an effective and eco-friendly method. To extract and concentrate copper, we use a technique with a deep tactic solvent, DES, and emulsification agent. We test the accuracy with this method by spike the T sample with known amounts of copper. The recovery rates showed good results, confirming the method's reliability. To further improve the accuracy, we use a matching calibration technique. This made the result even more precise. Overall, this method proved to be a trustworthy and innovative way to measure copper levels in rose T samples.
Assalamualaikum and hi. My name is Shashamara Minti Ilyas, and I'm really excited to share insights on the analytical technique FAAS, particularly focusing on its advantages, limitation, and recommendation for improvement. So let's begin by discussing the advantages of FAAS. First and foremost, FAAS is a cost-effective analytical technique. It is relatively affordable compared to other instrumental methods, making it especially suitable for routine analysis in laboratories with budget constraints. Next, FAAS requires only a small volume of sample for analysis. This advantage is particularly significant for conserving precious or limited sample quantities while still maintaining analytical accuracy. Finally, FAAS is environmentally friendly. By minimizing the use of organic solvent, it stands out as a more sustainable option compared to conventional liquid-liquid extraction techniques. Now, while FAAS has several advantages, it's important to recognize its limitation. To begin with, FAS is not suitable for analyzing multiple elements simultaneously. This limitation reduces its versatility for application requiring multi-element analysis. Additionally, FAS is prone to matrix interference. This is due to its narrow wavelength range and exposure to background radiation, which can lead to inaccuracies in the results obtained. Another drawback is its low sensitivity. The sensitivity of FAS, such as the sample matrix, instrument configuration, and the specific element being analyzed, unfortunately, its relatively high detection limits make it challenging for analyze trace level samples effectively. Lastly, FAS has a long analysis time. Since each sample must be analyzed individually, it becomes time-consuming, especially for laboratories that require rapid sample analysis. Moving forward, let me highlight a few recommendations to address this limitation and improve the performance of FAS. Firstly, improving samples preparation techniques can significantly enhance copper extraction efficiency. This step ensures better results during analysis. Secondly, optimizing FAS conditions such as temperature and wavelength can lead to greater sensitivity and more accurate copper detection. In addition, conducting thorough the method validation studies is crucial. These studies should assess parameters like linearity, precision, accuracy, and detection limits to ensure that the FAS method delivers reliable performance. Moreover, implementing a comprehensive quality assurance program can enhance the reliability and reproducibility of FAS measurement. Finally, adopting proper data analysis methods will help interpret FAS results more accurately, minimizing errors and improving decision making. In conclusion, the study aimed to develop an accurate and practical analytical method, FAS, to determine copper levels in roasty samples by optimizing experimental conditions, validating analytical performance, and utilizing a matrix matching calibration strategy. The method successfully achieved precise copper quantification in T matrices. This research not only addresses the need for assess copper content in roasty, but also contributes the broader food, safety, and quality control efforts within the tea industry. Thank you for your attention. Assalamualaikum and goodbye.